So training a single neuron model. A single neuron model looks like this. We have only one neuron, and let's say there are inputs coming like this. This is xi1, xi2, xi3, xi4. This is w1, w2, w3 and w4, and this is function f, and this is output, which is, let's say, yi hat. So we have a data point xi comma yi, right? We are feeding this input here. Xi has 4 features, or it is 4-dimensional data point, and we expect out to be very close to this yi. So the actual output produced is yi hat, and the actual output is yi. So if this yi hat is very close to yi, the prediction is very good. So now, how to train this single neuron model? So in order to train this single neuron model, we find the weights, which we find the training the single neuron model means finding the correct weights. So now for this discussion, we will consider a regression problem. So in case of regression, we know yi hat is equal to w transpose xi, right? So this is yi hat. So because in case of linear regression, so this yi hat is simply sum of these weights and inputs. So I can write this as yi hat as summation over sum over I is equal to 1 to n wi xi, or this is j is equal to 1 to n wj xi xij, right? Because this, let's say if this is wj, and if I write this data point as xij, when j is 1, so this becomes w1 x1 xi1. When j is 2, this becomes w2 xi2. That means this is multiplied with this is multiplied with this, and then these all terms are added, right? So this is what it means. So finding so training the single neuron model means finding the weights. Training any neural network means finding the correct weights, right? So for the discussion, we are considering this neuron solving a regression problem, right? So now let us write the loss function for this. So the loss is equal to yi. So if this is, let's say, loss I for ith input, loss for ith input is equal to yi minus yi hat. So this yi is the actual output, and this yi hat is the output produced by our model. So if this yi is yi hat is very different from this yi, we will get a bigger loss or greater loss, right? So we want this difference to be very less, right? So we want to minimize this difference. So total loss is equal to sum over I is equal to 1 to n. There are n data points, so it is li, right? So this is total loss, right? So we want to minimize this total loss, right? Now this yi hat for this linear regression, yi hat is equal to sum over I is equal to 1 to n j is equal to 1 to n wj xij, right? Or it is nothing but w transpose xi. Same term I can write like this, because this is vector representation of this term. So now so if I write the loss for linear regression, so li is equal to yi minus w transpose xi, right? So this will be the loss for linear regression. Now if I generalize this loss for any model, for any neuron model, maybe logistic regression, linear regression, or any other model, so the loss will be li is equal to yi minus f of w transpose xi. So this w transpose xi is the weighted sum here in this neuron model, right? So this sum wi's multiplied with xi's, so this sum w transpose xi. So if this, in general, this f will be f will be this function will be, or this y hat will be, this y hat in general will be f of w transpose xi, right? For linear regression, this will be this function is identity function in case of linear regression. That means this term will be w transpose xi. That means output input given to this function will be passed as it is to the output. And for logistic regression, if this f is sigmoid, then it becomes a logistic regression, right? So we have this loss now. Loss, go to the new page. So loss is equal to, in general, yi loss summation over I is equal to 1 to n yi minus f of w transpose xi. So this is the loss function. This is the loss function. And now for linear regression, this is a squared loss. This is a squared loss in case of linear regression. This is a squared loss, right? So here also this loss is squared loss in case of linear regression, right? So this is a squared loss everywhere. Now let us so after the step one is write the loss function. So now I am writing the steps for training the neuron model. Training the neuron means finding the correct weights. So first step is define the loss function, write the loss function. So this is our loss function, general loss function. The second step is write the optimization problem, right? The optimization problem. So here we want to minimize this loss, Now what can minimize this loss? See, in this equation, this yi and xi are fixed because they are input mapped with output. Only variable is w. Only this w can change. That means we want to find a w which will minimize this, right? So we want to find a w which will minimize. We want to find a w which will minimize this loss, right? Loss, which is nothing but summation over I is equal to 1 to n yi minus f of w transpose xi square, right? So we want to minimize this loss, right? So such w, let us call it as w star. We want to find a w star which will minimize this loss, right? Now how to solve this optimization problem? So this is the optimization problem. We want to find a w or weight which will minimize the loss. So see, in the training process we said that we will have a square loss. We define that loss and then we posed it as an optimization problem, saying that we want to find a w which will minimize this loss, we want to find all w's which will minimize this loss. Now let us see how to solve this problem. To solve this problem, we will use gradient descent or stochastic gradient descent, right? So stochastic gradient descent or gradient descent, right? So what we do in this gradient descent, we will initialize, first we'll initialize weights. So this will be random initialization. We'll initialize the weights w1, w2 randomly, right? Then we will compute the new w new is equal to w old minus eta. This is called as learning rate, right? So then derivative of this represents derivative of loss with respect to w old, derivative of loss with respect to w old. So new weight is equal to old weight minus eta time derivative of old weight, right? So now let us see how to compute this. If I represent this in this is vector representation. If I represent it in the scalar format, so this wi ith weight is equal wi new is equal to wi old minus eta times derivative of loss with respect to wi old. So that is how we can compute the derivatives. Now that is how we can compute the new weights. Now the question is how to compute these derivatives. That's the question, how to compute this derivative. So let us see how to compute this derivative. So if once we get this derivative, computing new weights is easy. Now and these weights will be updated till the convergence, right? Till the convergence. So let's see how to compute these weights. So also derivatives. So we want to compute dou L by this dou W. Right? So this, now if we see at the neuron model, here we have this W1, W2, W3, Wn. So this is xi1, xi2, xi3, xi4, f, and this is yi hat, right? And then this yi hat will be translated into loss. So we want to compute this loss with respect to derivative of this loss with respect to this w, right? So that means we want to compute this, right? So now by using the chain rule, we have dou L by dou W is equal to dou L by dou F and this dou F by dou W1, right? So if I write dou L, let's write it for W1, dou L by dou W1 is equal to dou L by dou F into dou F by dou W1, right? So compute this derivative, then compute this derivative, right? Now what is this dou L by dou F, right? Let's compute dou L by dou F. We know F is equal to so we know L is equal to loss function we have defined here. So this is our loss function. Let's write this loss function again, or I can compute the derivative here itself. So dou L by dou W1 is equal to, so let me go here. So dou L by, we want to compute this dou L by dou F. So L is equal to summation over I is equal to 1 to n. So Li yi minus f of W transpose xi whole square. So that is the loss function. We want to differentiate this loss function. We want to differentiate this loss function with respect to this f, right? So if I take dou L by dou F is equal to, in differentiation, this power comes down, so it becomes 2 times. So if I take a loss of ith, let me take the loss of ith data point, right? Ith data point. So dou Li by dou W1, right? Rather than finding the complete loss, I will compute the loss of a single data point. So dou Li by dou W1 so is equal to dou Li by dou F divided by into dou F by dou W1. So dou L by dou F is equal to, so this will be Li, right? So 2 times, in derivative this power comes down, 2 times yi minus f of W transpose xi, right? And now we will differentiate this term also, dou F by if we take the derivative of this term, right? If we take the derivative of this term, the derivative of this term will be 0, and for this term it will be -1, because this is f, right? We are differentiating with respect to f. Differentiation of x with respect to x is equal to 1, or differentiation of f with respect to f will be 1. So this now because of this minus term, we will have this minus term here, right? Okay, so now let's see how to compute this derivative. So this derivative in fact is xi. This derivative in fact is xi, because we have sum here. So what is the differentiation of f? F is nothing but output of sum over I is equal to 1 to n wi xi, right? So xi differentiated with this w, so that is nothing but xi, right? So this derivative is xi, right? So now if we compute this derivative, this is nothing but so dou L by dou Wi, dou Li, dou Li divided by dou W1 is equal to we had this dou Li by dou F into dou F by dou W1. So this term is equal to -2 times Li yi minus f of W transpose xi, right, into this is xi. So this is the derivative of this, right? So similarly, we can compute the derivatives of all the weights, and thus we can update the weights. Now I can update the weight W1. I can update the weight W1 using this loss, right? So in case of now, we can use SGD or gradient descent. In gradient descent, we use all the xi's and yi's to compute the derivative. In case of stochastic gradient descent, we can use one data point to compute the derivatives, right? Or I can take the batch of data points to compute the derivative. That is called as batch SGD. Okay, so this was how to train a single neuron model. Training a single neuron model means defining the finding the correct weights, right? So updating the weights, right? So that is nothing but training the single neuron model. So to update the weights, we first need to define the loss function, right? After defining the loss function, find the derivative of this loss function with or write the optimization problem. After writing the optimization problem, use the stochastic gradient descent or gradient descent, in which we compute the derivatives of this loss function with respect to weight, and use the derivative to update the weights. W, by using this formula, W nu is equal to W old minus eta. So this is learning rate. We'll see later how to define this learning rate. So eta times dou L by dou W old. Okay.